the combined gas law. The combined gas law is P1 times V1 over T1 equals P2 times V2 divided by T2. I consider this the best gas law because it incorporates Boyle's law, Charles' law, and Gay-Lussac's law all in one equation. If you take a look at it and let's say you erase T for a second, you have Boyle's law. And if you now put the T's back in, but let's say you erase P, now you have Charles' law. V1 over T1 is V2 over T2. Let's put that back in. P1 and P2. And obviously if you erase V1 and you just have P1 divided by T1 over P2 divided by T2, well, now you have Gay-Lussac's law. So the combined gas law, it combines all three gas laws into one law, and you can use it for pretty much any gas problem, and I'll show you how to do that right now. This is a typical combined gas law problem. A 700 milliliter gas sample at STP is compressed to a volume of 200 milliliters, and the temperature is increased to 30 degrees Celsius. What is the new pressure of the gas in kilopascals? The first step is to write the equation that you're going to use. In this case, it's the combined gas law equation. P1 times V1 over T1 equals P2 times V2 over T2. The next step is to write your knowns and unknowns. So we have all of these variables, P1, V1, T1, as well as P2, V2, and T2. Reading the problem over, we can find the initial pressure, volume, and temperature. It states a 700 milliliter gas sample at STP is compressed. So the initial conditions are the volume is 700 milliliters. The temperature and pressure are at STP. So what does that mean? Well, the pressure is 1 atmosphere at STP, and the temperature is 0 degrees Celsius. So let's fill in this data now. To find the final volume, pressure, and temperature, we look at the rest of the problem, and it says the gas is compressed to a volume of 200 milliliters. So we know that the final volume is 200 milliliters. It states that the temperature is increased to 30 degrees Celsius. So we're going to put our final temperature as 30 degrees Celsius. And the question states, what is the new pressure of the gas in kilopascals? So we're going to write our new pressure as X because we don't know what it is, and our unit is kilopascals. If you look at the variables very carefully, you should notice that the pressure 1 and pressure 2 are in different units. If we're trying to solve for pressure in kilopascals, it'd be wise to change pressure 1 into kilopascals as well. You should already know that 1 atmosphere is equal to 101.3 kilopascals. We're going to use what we know here, and what we're going to do is we're going to change the atmospheres by multiplying by a fraction using this information. We must put atmospheres on the bottom to cancel, so 1 atm on the bottom, and kilopascals on top, 101.3 kilopascals, and doing the math, 1 times 101.3 divided by 1 gives you 101.3 kilopascals. Next we'll look at volume. Volume 1 is 700 milliliters, and volume 2 is 200 milliliters. They're both of the same unit, so volume can be either in milliliters or liters as long as both volume 1, the initial volume, and volume 2, the final volume, are in the same units, which they are in this case, so we don't have to change either of the volumes. One thing you need to know for all the gas laws is temperature always has to be in Kelvin, because Kelvin is the unit that represents the average kinetic energy of particles, and it's very important that temperature gets converted to the units of Kelvin. In order to do this, in this case, the first temperature is 0 degrees Celsius. If we add 273 to that, we get 273 Kelvin. Whatever initial temperature you have in Celsius, whenever you add 273 to it, it can change it to the temperature in Kelvin. Our other temperature, temperature 2, or the final temperature, is 30 degrees Celsius. So if we add 273 to this temperature, it comes out to be 303 Kelvin. So these are the numbers that we're going to use and plug in to our combined gas law equation. Plugging in the numbers to the combined gas law equation, P1 is 101.3 kilopascals times volume 1, 700.0 milliliters. Temperature 1, 273 Kelvin, equals pressure 2, x kilopascals, volume 2, 200 milliliters, over 303 Kelvin. The first thing I would do in this case to solve the problem is cross multiply. So I would take the numerator of one side and multiply it by the denominator of the other side, or at least set it up that way, and the denominator of one side and multiply it by the numerator of the other side. If we do this, we get 101.3 kilopascals times 700.0 milliliters times 303 Kelvin equals 273 Kelvin times x times 200.0 milliliters. So now we don't have any denominators, which is much easier to work with. So if you multiply this first part out, it comes to a rather large number. The number is 21,485,730 kilopascals times milliliters times Kelvin. It's a bizarre unit, but that's what you did. You multiplied all those numbers together, and that's the unit multiplied out. So this is equal to, and then you multiply 273 Kelvin times 200 milliliters, and the number you get is 54,600, and that's Kelvin times milliliters. And then you also have this in parentheses times x kilopascals. The next step, in order to get x by itself, you need to divide each side by the 54,600 Kelvin times milliliters, and on this side you divide by the same thing, 54,600 Kelvin times milliliters. And on the right side, these two completely cancel each other out. The units and the numbers, everything cancels. The only thing that's left on the right side is X in the unit kilopascals. On the left side, well, the units milliliters cancel, the units Kelvin cancel, and the only unit that doesn't cancel is kilopascals. And then the next step is you need to divide the top number divided by the bottom number, and that gives you 393.5115 kilopascals. Alright, now we need to go back and check what are the correct number of significant figures that we should use for a final answer in this problem. Looking back at the original problem, you can see there's 4 significant digits here, there's 4 significant digits here, and there's 3 significant digits here. So the final answer should be up to 3 significant digits. In order to do this, we need to change 393.5115, and we're only going to focus on the first 3 digits. The 4th digit, does it round this 3 up? Yes. So I'm going to put x equals 394 kilopascals. And that's how you solve a combined gas law problem. It's really useful because if there's a lot of things changing, such as in this case the volume was changing and the temperature was also changing from 0 degrees Celsius to 30 degrees Celsius. So there was a lot of changes in both volume and temperature, and so if that, in this case, the combined gas law will help you solve those problems when there's 2 variables changing, and you're solving for, in this case, the variable of pressure, and we were able to solve that with no problem using the combined gas law equation. I hope you understand how to use the combined gas law equation, and never forget, always put your temperature in Kelvin. That's the key mistake a lot of people make. Remember, always put temperature in Kelvin.